This is part 3 of Module 14, where we complete our discussion on transformers. In addition to their use in the distribution of electric power, okay, there are many other uses of transformers. Transformers, for example, are also used in electronic circuits. One important application of a transformer is for impedance matching. This is an example of an impedance matching setup, where the impedance of a speaker is matched to the output impedance of an amplifier. We're going to take up impedance matching in more detail in the next slide. Another use of a transformer is to eliminate the DC component of signals. You will recall that in a transformer, okay, it is only the AC component of the signal that is applied to the primary that is able to induce a voltage across the secondary. Any DC component of an input signal will not create a changing magnetic flux. Thus, it will have no effect on the output. Okay, so expect the output to only consist of an AC component. And then another important use of a transformer is for electrical isolation. Remember that in a standard transformer, there is no wire that connects the primary side to the secondary side. The only thing that connects the primary to the secondary is magnetic flux. So if you have high voltages at the primary side, but if you are working at the secondary side, then you're protected from the primary. You're somewhat protected from the primary. Okay? So this is used a lot in power supplies, for example. Finally, you have transformers that are used in instrumentation. This is a current transformer. The conductor in a current transformer goes through the hole of this donut-shaped toroid. Okay. That donut actually picks up the magnetic field caused by the current flowing in that cable. And there will be an induced voltage across it, and you can measure the current flowing through the cable because it will be proportional to that induced voltage. Let's discuss impedance matching. Consider the circuit shown. The power delivered to the load, so this is our load, is maximum when RL is equal to RS. Let's say P of L is the power delivered to RL. If we try to plot that, P of L versus the value of R of L, when R of L is equal to 0, the power is equal to 0, because the voltage across R of L will be equal to 0. When R of L is equal to infinity, meaning open circuit, the power will also be equal to 0 because the current will be 0. So your curve will look something like this. It's asymptotic. Okay. The power maximizes when R of L is equal to R of S. This expression. Let's say R of L is not equal to R of S. How do we ensure that maximum power will be delivered to R of L? Well, what we do is we use a matching transformer. And this is our setup. This is the matching transformer. In the primary side, R of L is seen by the source as R of L prime, which is equal to N1 over N2 squared times R of L. So this is just the value of R of L referred to the primary side. If R of L prime is equal to R of S, then we have maximum power. So what we need to do is we need to adjust N1 over N2 so that Rs of L prime will be equal to Rs of S. Let's take an example. The output stage of an audio amplifier has an output resistance of 2 kilo ohms. Okay, so you have an amplifier, you're supposed to connect a speaker to that amplifier. The amplifier has an output resistance of 2 kilo ohms. This is, you might think of this as the Thevenin resistance of the Thevenin equivalent of the amplifier. An output transformer is needed to provide impedance matching with a 6 ohm speaker. If we just connect the 6 ohm speaker to the output of the amplifier, there's going to be very little power that will be delivered to the 6 ohm speaker. So if this transformer has 400 turns in the primary, how many turns must its secondary have? So this is going to be our scheme. This is the equivalent circuit of the amplifier. And this represents our speaker. So Rs is equal to 2K, RL is equal to 6 ohms. We have to make the value of RL referred to the primary equal to Rs. And you do that using the formula Rs is equal to N1 over N2 squared times RL. Okay, so plugging in values, 2000 equal to N1 over N2 squared times 6, we know that N1 has 400 turns, so we need to wind approximately 22 turns in the secondary. That is for the speaker now to receive maximum power from the amplifier. Okay. So this is something quite practical. So far, we've been talking about ideal transformers. What are the characteristics of a practical transformer? So this is now non-ideal. So we go back to the basic two-winding transformer, which we already discussed. First, if this is a practical transformer, both coils will have a small resistance. So like I told you, it's impossible for the windings not to have any resistance. These are so many turns. If you unravel these windings, of course, they will be very long and they will have resistance. Second, leakage flux will exist in both coils. So our assumption is that all the flux produced by coil 1 will flow through the core. And all the counter flux produced by coil 2 will also flow through the core. But that is not the case. No? There is some flux. Let me change my color here. There is some flux that will flow this way. Same here. And even in between windings, there might be some flux here. So this is your leakage flux. That's why when you wind transformers, you have to wind it very, very tightly because you want to avoid the flux that leaks in between windings. But you can't do anything about the flux that leaks into the air, no, across the entire winding. There is resistance loss in the core. Okay. If you touch the core of a transformer, even if there is no load connected, you're going to find that it is probably going to be warm or even hot. If it is a poor core material, it's even going to be hot. So there are losses. There are watt losses around the core, and that can be modeled by a resistance loss. And finally, the permeability of the core is high. Okay. Permeability, that is the property of the core to support the flow of flux. This is high, but not infinite. Thus, the exciting current is not equal to 0. If our exciting current is equal to 0, if we had 0 load, then I1 would be equal to 0. But we know that's not the case. No? If we take out the load, there's still a small value of I1 that will flow, which is needed to push magnetic flux to run around the core. This is the equivalent circuit of a practical transformer. R1 and X1 is the winding resistance and the leakage reactance of coil 1. So R1 represents the resistance of coil 1, X1 represents the component in coil 1 that takes into account the leakage flux. R2 and X2 are the corresponding values for coil 2. R2 is the winding resistance of coil 2 and X2 takes into account the leakage flux in coil 2. RC and XM are for modeling the core. RC models the heat loss in the core, and XM models the magnetizing current required for magnetic flux to flow around the core. Notice that this has been referred to the primary side. This could very well have been referred to the secondary side. In many cases, RC and XM are very negligible. So in many cases, we can actually do away with this. To take into account the power lost in the core, sometimes that is specified as a fixed parameter of the transformer. So in the nameplate rating of the transformer, it will just say, at full load, the transformer has losses of, let's say, 50 watts, or if it's a power transformer, a few hundred watts or so. So if you neglect RC and XM, this becomes our equivalent circuit. So we just took this out. Okay. The relationship E1 over E2 equal N1 over N2 applies to the center portion. Remember, this is now our entire transformer. This is our real transformer. But at the heart of our real transformer is still an ideal transformer. So the relationship E1 over E2 equal N1 over N2 and I1 over I2 equal to N2 over N1 still applies to the heart of our real transformer, which is an ideal transformer. It is possible to refer all impedances to the primary side of the transformer. In other words, we can refer this impedance and this voltage to the primary. And this is the equivalent circuit now which we're going to get. So what is our equivalent? Our equivalent is R1 plus turns ratio squared times R2. So this is R2 referred to the primary. X equivalent is X1 plus turns ratio squared times X2. And the voltage V2 referred to the primary is just A times V2, where A is our, again, turns ratio. A is equal to N1 over N2. So sometimes we're going to see this in the nameplate. And it's going to say, okay, R equivalent is so many ohms, X equivalent is so many ohms, refer to the primary or refer to the secondary. Okay? Because it is also possible to refer all the impedances to the secondary side instead of to the primary side. You should be able to do that on your own. Let's take an example. A single-phase transformer has the following nameplate ratings. No? The volt-ampere rating is 50 kilovolt amperes. The voltage rating is 7620 to 230 volts. and the equivalent impedance of the transformer is 0.03 plus J 0.04 ohms referred to the low voltage side. So in this case, it is referred to the low voltage side. The transformer supplies 30 kilowatts at 0.85 power factor lag to a load whose voltage is 225 volts. So we're supposed to find the input voltage, the power and reactive power supplied by the source, and the efficiency of the system. Okay, the solution which I'm going to present now uses power balancing with the source voltage referred to the low voltage side. So this is going to be my equivalent circuit. No? This is my load, which has already been specified as 30 kilowatts, 0.85 power factor lag, voltage of 225 volts RMS. This is my equivalent impedance, which, according to the nameplate rating, is already referred to the low voltage side. So what I have to do is refer V sub S to the load voltage side, and that is V sub S prime. Okay. Anyway, before doing that, let's complete the information on the load. From the load power triangle, if you do the power triangle of the load, you have Q of load is equal to P sub L, arctangent of arc cosine of 0.85, which will give me 18592.33 vars. And we also know that S of L, this is the apparent power that is absorbed by the load. This is P sub L over the power factor of the load. So P sub L is 30,000 watts divided by 0.85. I'm going to get 35294.12 volt amperes. From S of L, I can determine I sub L. No? Remember that S of L is equal to I sub L times V sub L. Therefore, I sub L will be S of L over V sub L. So that is, we computed 35294.12 volt amperes divided by 225 volts, the load voltage, which is 156.86 amperes. Remember, we're working here with RMS values, not with phasors. Now, what are the power and reactive power supplied by the source? The power and reactive power supplied by the source is going to be the power that is lost, okay, in Z equivalent plus the power that is eventually delivered to the load. So the power supplied by the source is equal to the power that is lost in Z equivalent. What is that? That is I L squared R equivalent, where R equivalent is the resistance component of Z equivalent, plus the power that eventually is delivered to the load. I sub L, here, I sub L we have computed at 156.86 amperes. So this is 156.86 squared. R equivalent is 0.03, and P sub L is 30,000 watts. So I'm going to get 33738.18 watts. So this is one quantity that we have now solved. No? We're supposed to get power, reactive power, input voltage, and efficiency. I can do the same thing for reactive power. Q sub S is equal to IL squared X equivalent, the reactive component of the equivalent impedance of the transformer, plus Q sub L. So this is 156.86 squared. This is 0.04. plus, we previously computed 18542.33. Sorry, 18592.33. And I'm going to get 19576.57 var. Okay, so 2 down, 2 to go. Actually, I can already compute for efficiency. No? Efficiency is equal to my output power over my input power. No? My output power is the power that is delivered to the load, so that is 30 kilowatts. My input power is the power that is generated by the source, which is 30738.18 watts. This comes out to 0.976, which is 97.6%. No? Notice it is a high efficiency, and this is typical of transformers. Okay, so we have one thing remaining to determine, and that is the input voltage. How do I get the input voltage? I can get the input voltage because I can now compute for the apparent power that is delivered by the source. I know the power delivered by the source. I know the reactive power delivered by the source. I can get the apparent power delivered by the source. S of S, again, this is apparent power. This is not complex power. This is Vs prime, the value of the primary voltage referred, or the high voltage side voltage referred to the low voltage side, multiplied by I of L, which is Ps squared plus Qs squared. I know Ps, I know Qs, so I can compute this. This is 36442.80 volt amperes. Thus, Vs prime, okay, will be equal to S of S over I of L, which is 36442.80 divided by 156.86, and I'm going to get 232.32 volts. Okay, so what happened? No, we have 225 volts here. We're supplying 232.32 volts here. There is some voltage that is lost across the equivalent impedance of the transformer. But remember, this is Vs prime. Okay. We want to refer Vs back to the high voltage side. So referring Vs prime back to the high voltage side, okay, I have Vs is equal to Vs prime times the inverse of my turns ratio. So this is 7620 over 230, which will give me 7696.97 volts. So these are my answers. This is Vs. This is my piece of S, 30738. It's this. My Qs of S is 19577, and my efficiency is 97.6%. Is that the only way of solving the problem? No? As usual, it is not. So in this approach, I used power balancing. I did not deal with any phasors in this particular approach. What if I had wanted to use phasors? Let's do this, no? Let's use a phasor-based approach But this time, let's refer all quantities to the high voltage side. So let VL prime and Z equivalent prime be VL and Z equivalent referred to the high voltage side. Okay. My equivalent circuit is going to look as follows. I will have my source voltage V sub S I will have Z equivalent referred to the high voltage side, which is Z equivalent prime. And then I'm going to have my load, which is still 30 kilowatts and is still 0.85 power factor lag. But this time, the voltage across my load is going to be VL prime. Okay. And the current that will flow now through the circuit will be my source current, I sub S. Okay. VL prime is going to be equal to VL multiplied by my turns ratio. My turns ratio is 7620 over 230. But VL is our reference phasor, which is 2 to 5 at an angle 0 degrees. This is our reference phasor. So I'm going to get VL prime is equal to 7454.35 at an angle 0 degrees. Z equivalent prime, on the other hand, will be my turns ratio 7620 over 230 squared multiplied by Z equivalent. And this will give me 32.93 plus J 43.91. And this is ohms. No? By the way, this is volts. Okay. I can use the complex power, or I can apply complex power to the load. Okay, I'm going to get S of L is equal to VL prime multiplied by IS conjugate. But I know this is equal to the power delivered to the load plus J times the reactive power delivered to the load. No? The power delivered to the load is 30 kilowatts, and the reactive power delivered to the load, which was previously computed, is 18592.33 VARs. So this is 30,000 plus J 18592.33 volt amperes. So I can compute for IS conjugate. That will be 30,000 plus J 18592.33 all over. Okay. V sub L prime is 7454.35 at an angle 0 degrees. And I'm going to get 4.73 at an angle 31.79 degrees amperes. Therefore, IS, my source voltage, will be 4.73 at an angle negative 31.79 degrees amperes. I know IS I know ZEQ prime, I know VL prime, I should be able to get VS from KVL. Okay? So KVL, VS, this is IS multiplied by ZEQ prime plus VL prime. Okay? This is 4.73 at an angle minus 31.79 degrees multiplied by ZEQ prime is 32.93 plus J 43.91 plus VL prime is 7454.35 at an angle 0 degrees. And using my calculator, I'm going to get 7696.97 at an angle 0.70 degrees. Again, we should expect V sub S to be greater than VL prime because there will be a voltage drop across Z equivalent. So I now know that this is V sub S, the RMS value of my source voltage. So that's one quantity that we've solved for. I can apply complex power to the source. S of S is equal to Vs, this is the voltage at the source, multiplied by Is conjugate. What is this? V sub S is 7696.97 at an angle 0.70 degrees multiplied by Is conjugate, which is 4.73 at an angle of 31.79 degrees. Expressing the result in rectangular form, this is 30,738.18 plus J 19576.57 volt amperes. And I know this must be the power delivered by my source, and thus this must be the reactive power delivered by my source. Efficiency now is equal to the output power over the input power. Our output, or what is delivered to the load, is 30 kilowatts. The input is 3738.18. This is 0.976 or 97.6%. So those are exactly the same values that we acquired or that we computed for in the first approach. Okay, to summarize the approaches we took, okay, there is your phasor-based approach, and there's also your power balancing approach. And notice that, okay, you can refer all quantities to the low voltage side, and you can refer all quantities referred to the high voltage side. Clearly, there are four possible combinations. Okay. So what we did in our first approach was all quantities were referred to the low voltage side and we used power balancing. What we did in the second approach was all quantities referred to the high voltage side, okay, and we used a phasor-based approach. But clearly, you could have done this approach or you could have done this approach. So that ends this module on transformers. This is not. This was not intended to be a comprehensive module on transformers. It's supposed to give you working knowledge of transformers. You're going to learn more about transformers in your future courses in EEE. Thank you.